So I'm going to find the dimensions of a closed 800 cubic meter cylindrical oil storage tank that can be made from the least amount of sheet metal. So I'm going to try to minimize the amount of metal being used to make a cylinder. So let me go ahead and sketch my cylinder real quick. All right, there's my cylinder. We know that every cylinder should have a radius and a height, and we know that the volume of this thing is supposed to contain 800 cubic meters. Now again, the purpose of this is to try to minimize the amount of metal that is used for, in this situation, the top, the bottom, and the sides of this cylinder. So we know that, again, the volume is supposed to be 800 cubic meters, and the volume formula for a cylinder is pi r squared h. So that is going to be my auxiliary function. And the thing that we are trying to minimize is essentially the surface area of this cylinder. So we're going to write down surface area equals 2 pi r squared, because that's the top and the bottom, plus 2 pi r h, because that's the sides of the cylinder. Now, again, this is our objective function. This is what we're trying to minimize. And again, r is our radius, h is our height. So the first thing I want to do is to try to use, again, our auxiliary function to figure out how I can rewrite this objective function as one variable. So what I'm going to do is I'm going to go ahead and plug in the 800 equals pi r squared h. And in this situation, the h is probably the easiest thing to solve for, so I'll just divide everything by that pi r squared. Pi r squared equals h. And I've got this, which we can plug in up here. So my rewritten objective function is going to be 2 pi r squared plus 2 pi r times 800 over pi r squared. Now, this pi and this pi will cancel out. R on top and one of the r's on bottom will cancel out. So it simplifies down to 2 pi r squared plus essentially 2 times 800, which is 1600, all over just one r. When I go to take the derivative, it might be easier to at least recognize that this is the same thing as 2 pi r squared plus 1600 r to the negative 1. So now that I've got all that taken care of, one of the other things that I probably should think about at some point is considering what the domain of r should be, just realistically. So for example, I really could consider that r is 0, that the radius is 0. That doesn't really make a cylinder, so I'm just going to use an open bracket here just because, again, it doesn't it doesn't realistically happen. You can't have a cylinder with a radius of 0. The other thing that I'm going to consider is, if r is the biggest possible number here, uh, what thing could I use to kind of make it the 800, realistically speaking? Well, in that situation, I probably could say, the square root of 800 might be reasonable, but it's not really, because technically speaking, as long as h is any positive number, the r could keep going on and on and on. So there really isn't, I'm going to say, a true maximum value to this. Again, there's nothing really stopping me from plugging in something really, really big and just having a really, really small height. Um, but so in this situation, I do want to think about taking the derivative of my uh, objective function with that one variable in it. So I'm going to go back to taking this derivative. And so r squared is going to become 2r when I take its derivative. When I multiply that by 2 pi, it'll be 4 pi r. And that is going to use the power rule, so the negative 1 is going to come out front, so it's going to be minus 1600 r to the negative second, which you could also consider that as 4 pi r minus 1600 over r squared. Again, I want to point out that this function is not defined for r equals 0, which is kind of why I used an open bracket there, not a closed bracket. So again, my derivative is undefined when r equals 0, but that's not realistic, so I'm going to ignore that as a critical value. I do want to figure out where the rest of this derivative is equal to 0, so let me come over here and see 0 equals 4 pi r minus 1600 over r squared. I'm going to move the negative thing over to the other side, so it's going to be 1600 over r squared equals 4 pi r. Multiply by r squared on both sides, we're going to get 1600 equals 4 pi r cubed. Move my screen down a little bit. Divide by the 4 pi. 16 divided by 4 is 4. Keep the double zeros. All over pi equals r cubed. Then we need to cube root it. So 400 over pi's cube root is r. So there's my critical number. And what I need to do at this point is use either the first derivative test or the second derivative test to figure out, is this a maximum or a minimum? I'm hoping that, again, it is the minimum because I'm looking for the least amount. And so I'm just going to do the first derivative test because I've already got the first derivative. So I'll draw myself a little number line. Again, we know that 0 is kind of realistically the minimum here. We couldn't have 0 even if we tried. And then I'll put the cube root of 400 over pi here. Now, I'm going to go ahead and type that into the calculator and figure out what the cube root of 400 over pi is. Let's see, 400 divided by pi, and then cube root it. We get approximately 5.03 and some change. So a good sample point, a good number to test would probably be 5. And let's try, oh, let's just do 5.5. And again, we're going to plug this into our first derivative, which is over here. So let me do that. 4 pi times 5 minus 1600 divided by 5 squared gives me a derivative value of negative 1.17 if I round. So I know that this section is negative. And then if I plug in 5.5, bear with me while I type in my calculator, 5.5, I got a derivative value of 16.22. So that makes this positive, which means according to the first derivative test, this critical number right here should be a local minimum, which is exactly what I wanted it to be. And so let me go back and read the rest of the questions. Find the dimensions of a closed 800 cubic meter cylindrical oil storage tank that can be made from the least amount of sheet metal, assuming there's no wasted material. So I do have the radius, which is that cube root of 400 over pi, which is one of the things I need. So let me write that. Answer, the radius is the cube root of 400 over pi. But it wanted the dimensions, so I still need to go back and plug this in to find the height. Well, good for us. We have this auxiliary function here where all I have to do is plug in that cube root in for r, and I can just calculate the rest of that. So let me go ahead and type into my calculator 800 divided by parentheses pi times that cube root of 400 over pi as a cube root. And I got to make sure all that is in my denominator. Let's see what happens. Oh, I forgot to square it. That's what I forgot to do. I got to make sure I square it. That was an r squared down there on the bottom. So like I said, what I'm doing on my calculator is 800 divided by pi times the cube root of 400 over pi squared, which gives me about 10 point, whoop, I ran out of room. Gives me about 10.06. So my dimensions should be about 5.03, 5.03 as my radius, and a height of about 10.06. And that should make the least amount of sheet metal. Hopefully that helps you guys with any problems that you're having. Let me know if you have any questions. Bye.